Good morning, everyone. This is the second session of Chapter 3 Vibrational Spectra of Diatomic Molecules. Last time, I was trying to study the vibration of the atomic molecule quantum mechanically. So I've started with writing the energy of the atomic molecule, as usual, in terms of the atoms 1 and 2. And then what we have done is that we have changed the coordinates into new coordinates x and q. X represents the displacement of the center of mass and Q represents the vibration around the center of mass. So the corresponding Hamiltonian now is formed of two parts. One corresponds to the Hamiltonian of the motion of center of mass, and the second part corresponds to the Hamiltonian of the vibration around the center of mass. Because we are not interested in the translation of center of mass, so we take this part and write the Schrödinger equation in order to get the energy, which is only the vibrational energy of the molecule. Note that we have substituted for u half q squared, which is the approximation or the harmonic approximation of the potential energy in the case of a diatomic molecule. Now the solution of this Schrödinger equation, which gives the vibrational energy of a diatomic molecule, is not developed here in the course. We only care for its solution. It gives the solutions E nu equals h nu nu plus half, where this nu corresponds to the vibrational frequency of the bond, and this nu is a quantum number equals to 0, 1, 2, etc. According to the quantum mechanical treatment, we have found that the vibrational energy of the molecule can only possess discrete values. So these values are E0 will be equal to half h nu, E1 will be equal to 3 over 2 h nu, E2 will be equal to 5 over 2 h nu. Remember, I'm just using E nu equals nu plus half h nu. So I'm just using that. So here it's simply 0 plus half h nu. Here it is 1 plus half h nu, and here it is 2 plus half h nu. So you can see that the difference between two consecutive levels is equal to h nu. So the difference between level 0 and 1 will be h nu. The difference between 1 and 2 will be h nu. The difference between 2 and 3 also will be h nu. And here the first distance will be half h nu. هيدا الكونكلوجن اللي لقيناه نحن ما قدرنا نوصل له من خلال الكلاسيكال ميكانكس. بالكلاسيكال ميكانكس ما لقينا انه في كوانتايزيشن للانرجي، فكرمال هيك اضطرينا نروح صوب الكوانتم ميكانكس حتى نقدر نعمل كوانتايزيشن للانرجي. السبب انه الاوبزرفد سبيكتروم اللي نحن لقيناه كان فيه بقلبه different lines، يعني اكيد هيدول جايين من discrete values، فلكان انا لازم يكون عندي discrete energy. Let us try to understand this diagram represented here on the right. So this is the potential energy curve, and as you can see we have horizontal lines. These horizontal lines represent the vibrational energy of the molecule. So the vibrational energy can be, as we have said, half h nu, 3 over 2 h nu, 5 over 2 h nu, etc. So they are separated by h nu. So the line represents the vibrational energy of the molecule. You can see that it is drawn as function of r. R is the length of the bond or the internuclear distance. Re is the equilibrium distance. So when R is equal to Re, in this case, there is no stretching or compression of the bond, and all of this energy is totally kinetic. لما نكون عاملين maximum elongation, so the bond will have a certain length R, okay, and the total energy in this case is potential. How do we know? Because the energy is intersecting with the potential curve. That means the potential energy U is equal to the total energy E, and the kinetic energy in this case is equal to 0. Same in the case of maximum compression. So in the case of maximum compression, the graph of the potential energy meets the horizontal line, which determines the vibrational energy of the molecule. So the potential energy is equal to the energy of vibration, and the kinetic energy in this case is equal to 0. One last note is that from this diagram we can observe the minimum and the maximum elongations of the bond for each energy level. So you can see, for example, let's take this energy level. This is a new 1, this is a new equals 2, and this is a new equals 3. So let's take new equals 3 level. So we can find the maximum elongation of the bond. Let's call it R2, for example. And this is the minimum elongation of the bond R1. So you can see as the energy goes higher and higher, the range of elongation gets larger. So it's obvious from the shape of the parabola. Now, how classical description of the motion is different from quantum description of harmonic oscillator? The first difference between them is that according to classical description, the energy is continuous, while according to quantum description, the energy is quantized, and it's equal to nu plus half h nu. The second difference is that quantum mechanics predicts that extreme positions are less likely than positions near equilibrium, whereas classical mechanics predicts exactly the opposite. So let's understand how does this happen. Here you can see we have drawn the wave functions. This is the wave function corresponding to this energy level or level nu equals 0. And this, which is represented by a solid line, is the wave function for the energy level 1, etc. And this is the wave function for the energy level 2. So the one in the dotted line, this one, represents psi squared. So this is the probability density. So the one in the solid line is psi, and the one with the dotted lines is psi squared, the probability. So you can see that the probability of finding the particle in the energy level 0 is the highest in the middle. The probability of finding the particle is the highest here in these regions, anyway close to the origin. And for the second energy level, the highest probability is found here, approximately here and here. So this is according to quantum mechanics. You can see that for at least small quantum numbers 0, 1, 2, 3, 4, etc., we can see that the positions that are near the equilibrium position are more likely to be occupied. While according to classical mechanics, this is not the same. نحن بنعرف بالclassical mechanics when a particle is oscillating, so the particle is oscillating, at the center V بتكون max, so it has all its energy in the form of kinetic energy. At the extremities, V tends to be 0, so 0 at the extremities. So in reality, the particle is very fast in the middle and very slow at the extremities. So if it's going to spend some time, it will spend more time at the extremities than time in the middle, which is opposite to the thing shown using quantum mechanics. According to quantum mechanics, it's likely to be found in the middle and less likely to be found at the extremities. One last difference between quantum approach and the classical approach is that according to classical mechanics, the boundaries of maximum elongation and maximum compression are determined by the intersection between the potential graph and the energy graph. So if this is the energy graph, if this is the energy level we're talking about, the point of intersection between the energy level and the potential energy determine the maximum and the minimum elongation of the bond. However, according to quantum mechanics, there is still a small probability of finding the particle outside the potential well. According to classical mechanics, R maximum هو أكبر elongation, R minimum is the minimum elongation. ما بيقدر يتخطى R max أو ينزل تحت R minimum. بينما according to quantum mechanics بضل عنده الأوسيليتر فرصة إنه يكون ولو بجزء كتير صغير أو probability كتير صغيرة إنه يكون عنده R أكبر من R max أو R أصغر من R minimum. Probability كتير صغيرة, but it's still found. Now we are going to define the vibrational spectral term, similar to defining the rotational spectral term. So, to define the vibrational spectral term, it's enough to divide the vibrational energy in U by Hc. So when we divide E nu by hc, we get the vibrational spectral term, which is expressed as a wave number. And this wave number is denoted as G bar of nu. As you can see, E nu equals hc G bar nu, so that if we divide the energy by hc, we will get, so dividing h by h is cancelled, nu over c is equal to nu bar, and nu bar in this case is the vibrational wave number. It's equal to 1 over 2 pi c radical k over nu. In some books, this vibrational wave number is written as WE or omega E. It's just a notation. Now let's talk about the transition selection rules. The cross-selection rule for a change in vibrational state brought about by absorption or emission of radiation is that the electric dipole moment of the molecule must change when the atoms are displaced relative to one another. If I want to say the same sentence in other words, I'm going to say that if due to vibration, there is a change in the electric dipole moment of the molecule, so this change in dipole moment allows the absorption or emission of radiation. In these cases, these vibrations are called infrared active. Why infrared? Because vibrational spectra are found in the infrared region. Now in our course, we are interested in diatomic molecules, homonuclear and heteronuclear. In the case of homonuclear diatomic molecules, the dipole moments are zero. Why the dipole moments are zero? Simply because the distribution of charge is equal in both sides. So there is no separation between positive charges and negative charges, and this causes a zero dipole moment. While stretching of the bond during the vibration of the molecule, all the time there remains a symmetry between both sides, and all the time the dipole moment remains zero, which means that there is no change in the electric dipole moment, and hence homonuclear diatomic molecules are infrared inactive. They have no vibrational spectra. Now on the contrary, heteronuclear diatomic molecules are infrared active. Why? During the vibration of the molecule, there is a change in the center of mass of negative charges and center of mass of positive charges, which causes a change in the electric dipole moment, and hence our molecules are infrared active. Now this is the gross selection rule for transition. What is the specific selection rule? The specific selection rule is usually found using the wave functions of the eigenvalues. So we check for mu of I, which is mu is the electric dipole moment, for psi final, mu, psi initial, it must be different to zero, and we arrive to a condition. So they have found that delta nu must be equal to plus or minus 1 to get the transition electric moment different from zero. So delta nu equals plus 1 corresponds to the case of an absorption, and delta nu equals minus 1 corresponds to the case of an emission. So when the molecule moves to a higher energy level, so it means it has absorbed a photon and it moved to a higher energy level, and when the molecule moves to a lower energy level, it means that it lost a photon and moved to a lower level. For sure this lacks here d tau, and it must be the complex conjugate. Now let's check if our quantum mechanical approach based on a harmonic oscillator is in accordance with the observed experimental spectrum. So let's calculate the wave numbers of allowed vibrational transitions if we are going to go from a level nu to a level nu plus 1. You know, in the case of absorption, we're only allowed to go from a transition nu to transition nu plus 1 because delta nu must be equal to plus 1. So in this case, to calculate the wave number of allowed transitions, when we go from nu to nu plus 1, the wave number of the absorbed photon, nu bar, is equal to simply g bar nu plus 1 minus g bar of nu, which will be equal to, simply remember that g bar of nu, it's equal to nu bar nu plus half. So add just 1 here, it will be 3 over 2, and here it's G bar nu. So subtract, you will get nu bar. So this nu bar is the vibrational wave number of the bond. This nu bar here is the wave number of the absorbed photon when we go from level nu to nu plus 1. Whatever level we go in, if we go from 1 to 2, from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, etc. So we can see that the wave number of the absorbed photon when we go from level nu to level nu plus 1 is independent of nu. يعني ما بيهم من أي level لأي level رايح أنا، دايما عم يطلع معي الويف نمبر الابزوربد فوتون اللي هو هيدا بيساوي الفايبريشنال ويف نمبر اوف ذا بوند خاصة بالاوسيليشن للبوند. Okay, so according to these observations we have only a single wave number of the absorbed photons. يعني كل الفوتونز إذا ما عملون absorption راح يكونوا على نفس الويف نمبر اللي هي بتساوي الفايبريشنال ويف نمبر. So according to these, if I'm going to draw the absorption spectrum, there will be only one line that is situated at the nu bar. Nu bar is equal to the vibrational wave number of the bond, which is not in accordance with the experimental values. Remember that in the experiment we have found a line of high intensity in addition to smaller ones. So we have to think of something else. Maybe it's the harmonic oscillator. Maybe it's the potential energy function that doesn't. So let's see what we have to do. Why our predicted vibrational spectrum using quantum mechanics is different from the experimental spectrum? In our work, we have used a harmonic oscillator approximation. This harmonic oscillator approximation neglects two essential properties of real molecules. First, as you can see from the shape of the potential energy, it was like this. So this is the potential energy graph. This is a harmonic oscillator potential energy. This is the equilibrium bond length. So as the energy gets higher, so for a higher energy level, R will increase. R represents the length of the bond. This increase in the bond length has no limits, which is not even possible because we know that when two atoms are far enough, the bond between them will break. So there's something that's not just right. Again, according to the same approximation, for small values of R, as the energy goes higher, all values for contraction are available, which is also not real because you know that as the atoms become closer, it's hard to compress them more. So in reality, the function decreases much rapidly compared to the harmonic function. لكن نتيجة إنه نحن أخذنا parabolic approximation أو اعتبرنا إنه البوند هو مثل السبرينج رح يتصرف كهارمونيك اوسيليتر، البوتنشال تاعوله هو half kq squared شكله parabolic. هيدا كله أدى لمشكلتين. أول وحدة على large values of R مفترض يكون أنا في عندي dissociation، مش تضل الانرجي طالعة طلوع عادي كأنه ما في شيء، لازم يصير في dissociation للكيميكال بوند والاتومز كل وحدة تروح بحالها. وكمان على small values of R لما أنا يكون عندي الكompression كتير قوي، بهيدي الحالة مفترض ما يكون الكompression عادي كمان هارمونيك، لأنه نحن بنعرف إنه نحن بنوصل لمرحلة بصير الكompression كتير صعب، فلازم يكون في نوعا ما شيء متوافق مع الرياليتي. So to do this we have to consider anharmonic motion. What is the anharmonic motion? In this case we consider that the restoring force is no more proportional to the displacement. Yani we can no more say that F is equal to minus kx. We just neglect that and we try to use Taylor series and choose a potential function that's more realistic. هلا البارابوليك approximation هي true لأول كم level لأنه بيكون شكل الجراف البارابولا، بس بعدين للhigher values of higher energy levels بتصير كتير بعيدة عن الرياليتي. So let's see what we have to do. This is the Morse potential energy. One approach to the calculation of the energy levels in the presence of anharmonicity is to use a function that resembles to the true potential energy more closely. So, as you can see, this potential is more close to reality than the one we have taken. The Morse potential energy has this equation. U, the potential energy, equals hc d bar E, 1 minus exponential minus AR minus RE, all of it squared, where Q is equal to R minus RE, as we have seen it before. It measures the distortion of the bond from its equilibrium length. It measures the contraction or the relaxation of the bond. dE is the depth of the potential minimum. So this is dE from the graph. As you can see, it's the wave number. HCdE is simply the energy. So dE alone is the wave number in centimeter minus 1 or in meter minus 1. A is a constant. It's equal to radical mu omega squared over 2hc d bar E. The dE is the depth of the well. This constant A determines the narrowness of the potential well. So it determines how narrow it is from down. D0 bar is called the chemical dissociation energy of the molecule. As you can see, it starts from the level nu equals 0, from the ground level. dE bar is the depth of the potential well, and sometimes it's called spectroscopic dissociation energy of the molecule. So this one is the chemical dissociation energy, and this one is the spectroscopic dissociation energy. The difference between them is the 0 point energy of bond vibrations. So this is at nu equals 0, the energy E nu or E0 is equal to half h nu. So the difference between them is simply half h. So we can say HCdE is equal to HCd0 plus half h nu. Near the well, minimum of variation of U with displacement resembles a parabola, while at large displacement, the shape of U allows for dissociation. So if we look at this graph, we can see that down in this area here, for small values of mu, we can see that it's similar to a parabola. The parabolic approximation is okay. But at large values of displacement, for example, you can see that the potential tends to a constant value. It tends to an asymptote. It means that after a certain limit, the potential between the two atoms becomes constant, which means the chemical bond is dissociated. In this slide, we give a comparison between the harmonic potential energy and the Morse potential energy. You can see to the right the harmonic potential energy in green and the Morse potential energy in blue. So we observe a continuously smaller increase of the potential energy of the molecule as R increases beyond RE. So you can see that there is an increase in the potential energy, but this increases up to a limit. The limit is the dissociation energy. dE is defined as the energy to the bottom of the well, while D0 is defined as the dissociation energy till the level nu equals 0. Coming to small values of R, you can see that the blue line decreases more rapidly than the green line, which means that we are unable to bring two atoms very close to each other without being affected by the repulsion between these two atoms. So, Morse potential energy describes better reality than the harmonic oscillator. You can see that at low levels, nu equals 0, nu equals 1, nu equals 2. The difference between the green and the blue, it's not very far, so we can say they are approximately close. But at large values of R, small values of R, the difference appears clearly. We can write the Morse potential as you can see here. Small arrangement, we get 3 terms. So this first term is responsible for the repulsion at short distances. This term here is responsible for the attraction at large distances, and this is the asymptote as Q tends to infinity. So as Q, this is Q here, this is Q, R minus RE. So as Q tends to infinity, this term will be equal to 0, this term will be equal to 0, and U will tend to HCDE, which is the dissociation energy. Now, same as the previous steps, we are going to take the Morse potential, place it in the Schrödinger equation, try to find the solution of this Schrödinger equation. So the Schrödinger equation can be solved for the Morse potential, and the permitted energy levels are found to be E nu is equal to H nu nu plus half minus H nu xe nu plus half, all of it squared. So as you can see, there appears a term. This term was not found previously when we have taken the harmonic approximation. This new term appears in the unharmonic approximation when using Morse potential. Now again, I will remind you, this one is the frequency of the oscillator, the frequency of the vibration of the bond. Xe, for sure, it's 0, 1, etc. Xe is a constant with no dimensions. Xe is usually small. It's much smaller than 1. Xe is called the unharmonicity constant. It's unitless. And sometimes we give Xe times a nu bar. Nu bar is the vibrational wave number. Sometimes also we give Xe nu bar as the unharmonicity constant. This one has a unit centimeter minus 1. This one is unitless. So Xe is a constant. It's equal to a squared h bar over 2 mu omega. Omega is the angular frequency of oscillations or vibrations. It's equal to nu bar over 4 dE. Remember that this is the vibrational wave number of the bond, and this is the dissociation energy. تذكروا نحن كنا قايلين بالهارمونيك اوسيليشن انه الفرق ما بين اثنين levels، يعني إذا أنا بعمل جي نيو minus 1 plus 1 minus جي نيو رح يطلع معي نيو بار. نيو بار هي ال vibrational wave number of the bond. So الفرق ما بين اثنين levels ك wave numbers هو نيو بار. كenergy هي h نيو. Okay, so it's simply divide by hc. So الفرق ما بين اثنين levels ك wave numbers هو نيو بار. So نحن بنعرف انه من تحت لفوق من الصفر لعند ال dissociation energy هي الانرجي هي دي اي بار. So simply إذا أنا بقسم نيو بار على دي اي بار, the answer will be very small. Simply because لأنه دي هي الانرجي كلها من تحت لفوق, بينما نيو بار هي الانرجي ك wave number between two consecutive levels. هيدا إذا أنا عم بحكي عن الهارمونيك oscillation. But here it's closed, يعني في فرق شوي بالlevel, but it's similar to this. That's why nu bar over 4 dE is very small. Okay, so Xe or Xe nu bar is called the unharmonicity constant. Difference between them simply either it's given unitless or given in centimeter minus 1. Okay, now to find the vibrational spectral term, all we have to do is we divide the energy by Hc. Once we divide energy by Hc, we get G bar nu. So you can see that it's nu plus half nu bar. This term was found in the harmonic oscillator. And we have an additional term, this is the additional term, that appears due to the unharmonicity. So simply we divide here by Hc, we divide here by Hc to get G bar of nu. Now let's analyze the results that we have reached. We have reached an expression for G bar nu, or for the vibrational energy levels. According to these results, as nu increases, the separation between two consecutive levels is no more constant. It decreases as the energy level increases. So as you can see here, the difference between two consecutive levels is no more constant. It decreases with the increase in energy. Over that, we reach a maximum energy level. After this, there's no more vibration because the molecule will dissociate. This is according to Morse potential, which is also very close to reality. Now let's check the wave numbers of absorption, when the molecule moves from a level nu to level nu plus 1, because we want to compare our results with those of the experiment for sure. So let's calculate nu bar for a transition from nu to nu plus 1. This is the wave number of the absorbed photon, or the spectrum. It's simply G bar nu plus 1 minus G bar nu. So we substitute for G nu as we have found it for an anharmonic oscillator. So this is for G nu plus 1 and this is for G nu here. We substitute, we arrange, we get this form. You can see that as nu increases, nu bar spectrum will decrease, which means that the difference between the energy levels will decrease as the energy or the quantum number increases. Now this result means that we have not only a single peak, but we have several peaks. Why? Because we have different values for nu bar of the spectrum. For each value of nu quantum number, 0, 1, 2, etc. For each transition from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, etc. We have a nu bar of the spectrum different from each other. So let's see the distance between two consecutive peaks is how much. So if this is a certain peak, then the distance between two consecutive peaks is simply we just replace nu by nu plus 1. As you can see, I've only replaced nu by nu plus 1. It was nu plus 1, then I added 1 to get it like this, and I've subtracted them. The idea of that is I'm just trying to find the distance between two spectra on the graph of absorption, the separation of wave numbers between two consecutive lines. So it came out to be 2xe nu bar. This xe nu bar is the anharmonicity constant that we have seen in the previous slide. So each two consecutive lines are separated by a constant 2xe nu. But this, up till now, is not in accordance with the experiment. We did not see lines like these. We have seen a line and small lines. These small lines are not due to absorption spectra from different levels or from higher levels. They are simply due to absorption from the levels from 0 to 2, 0 to 3, etc. So due to anharmonicity, not only the transition rule delta nu equals plus or minus 1 is allowed, but also the rule delta nu equals plus or minus 2 and delta nu is equal to plus or minus 3. All transitions rule are okay for an anharmonic oscillator. Now, why does that happen? Because we have found delta nu equals plus or minus 1 using the wave functions of a harmonic oscillator. But now if I'm going to use the wave functions of an harmonic oscillator to find the selection rule, we're going to find that all transitions are allowed. So because all transitions are allowed for an anharmonic oscillator, according to quantum mechanics, we have seen that there are transitions from 0 to 2, from 0 to 3, but they are weak. Okay? The transition from 0 to 1 is high, but the transition from 0 to 2, from 0 to 3, etc. are very weak. بس رح ارجع أكد على اللي حكيته. الويف نمبر للسبكتروم بتعتمد على الكوانتوم نمبر نيو. يعني المسافة ما بين الانرجي ليفلز هي منا ثابتة، بتعتمد على نيو. كل ما نيو عليت كل ما المسافة ما بين الانرجي ليفلز صغرت، فلكن الفوتون أو الانرجي of the absorbed photon رح تصغر. كرمال هيك مش كل الابزوربد فوتونز عندهم نفس الانرجي. الانرجي تاعت الابزوربد فوتون بتعتمد على الكوانتوم نمبر نيو. So بالسبكتروم حسب as we are going to assume السبكتروم تاعولنا منه مؤلف من بيك وحدة، مؤلف من كذا بيك حسب النيو، حسب الترانزيشنز اللي عم يصيروا عنا. So إذا أنا بدي أشوف 2 peaks ورا بعض they must be separated by a value 2xe nu bar. ونيو بار هي ال vibrational wave number of the bond. هلا بالهارمونيك oscillator transition rule كانت delta nu equals plus or minus 1، بينما هيدي الحالة منا موجودة بالانهارمونيك oscillator. السبب إنه الويف فانكشن غير، هو الويف فانكشن غير، فالسelection rule هي غير. فلكن في حيلا ترانزيشن تصير. نحن لقينا إنه أغلب الترانزيشنز أو أكثر الترانزيشن المتداولين هن من الصفر للواحد، من الصفر للاثنين، من الصفر للثلاثة، أوكي؟ أو من الصفر للأربعة. ليش من الصفر على طول؟ لأنه أغلب الموليكولز بيكونوا هن بالستيت اللي هي زيرو. رح أشرحها هلأ بالسلايد اللي جاي. هلأ the other transitions are allowed، يعني ممكن من الواحد للثلاثة مسموح، من الاثنين للأربعة مسموح. all transitions are allowed، أوكي؟ بس أكتر شي common من الصفر للواحد، من الصفر للاثنين، ومن الصفر للثلاثة، أكيد من الصفر للأربعة. بس أكتر شي من الصفر للواحد، وبيجوا من الصفر لاثنين أقل منه، صفر لثلاثة أقل، والصفر للأربعة أقل كمان، يعني بصير يصغر ال probability of these absorptions. هلا ال other absorptions من 2 لل3 من 3 لل4 كمان هن موجودين، بس كمان باحتمالية أقل. السبب إنه الموليكول بالأساس هي بالحالة العادية أغلب وقتها بتكون بستيت زيرو، ففي احتمال ضئيل تنتقل من الواحد على الاثنين، لأنه هي بأغلب وقتها بالصفر، فأغلب الاحتمال تنتقل من الصفر على الواحد، أو من الصفر على اثنين، أو من الصفر على ثلاثة، وهكذا. So I will explain these شوي لقدام. So in the case of an anharmonic oscillator, we have said that other transitions delta nu equals plus or minus 2, plus or minus 3, etc. are possible in addition to the transition plus or minus 1. All of them are possible. But the difference is that plus or minus 1 has a highest probability, while plus or minus 2, plus or minus 3 have lower probabilities. And how are they confirmed? They are confirmed with experiments. From our experiment, we have seen the harmonics. They are called the harmonics, which are transitions with selection rule delta nu equals plus or minus 2, delta nu equals plus or minus 3, etc. So because mainly the molecule is found in the zero level, let's find the transition from 0 to 2, from 0 to 3, and the transition from 0 to 1 for sure, which is the fundamental transition. If the molecule is going from the energy level 0 to the energy level nu, then it's going to absorb a photon with wave number nu bar. Nu bar of the spectrum is equal to G bar nu minus G bar of 0. So just substitute G nu minus G 0, so substitute for nu 0, you will get this form. If you arrange, you get this form. So what I have done is that I have gathered the coefficients of the nu alone and the coefficients of the nu squared alone. So as you remember from the introductory part of this chapter, we have said that the experimental spectrum had wave numbers that were arranged in the form of B nu minus C nu squared. So in this case, B is simply this constant and C is simply this constant. So C represents this and B represents this. So if I'm going to draw the lines for a transition from 0 to level nu, I will draw lines that are related with this relation nu equals B nu minus C nu bar, which is similar to the experimental results that we have already seen at the beginning of this chapter. We have seen that the transition delta nu equals plus 1 has the highest probability. So just substitute for nu 1. Okay, so substitute 1. So you will get this equation. Now this is called the fundamental wave number. It's the wave number for a transition from 0 to 1, which is the most probable. Now the first harmonic is a transition from 0 to 2. Substitute for nu 2. So it's equal to 2 nu bar minus 6 xe nu bar. You can see that this is the first harmonic. This is the fundamental due to a transition from 0 to 1. This is due to a transition from 0 to 2. It has a lower probability. And this is due to a transition from 0 to 3, which has this equation 3 nu bar minus 12 xe nu bar. This is the second harmonic, and etc. if more peaks appear. So this conclusion is similar to the experimental spectrum that we have seen at the beginning. You must have noted that even for the quantum number nu equals 0, the lowest vibrational energy level, the energy of the molecule is never 0. So even if we substitute nu equals 0, the energy of the molecule is never equal to 0. This means that even in its lowest energy level, the molecule always vibrates. So in its lowest energy state, the molecule always possesses a small vibrational energy. It's called energy of the 0 point. Now in this slide, we are going to prove the formula of Bridges-Spooner. So we have seen earlier that Xe is equal to nu bar over 4 dE bar. So here I'm going to just prove dE bar is equal to nu bar over 4xe. So I'm going to prove this formula. So at the vicinity of the energy of dissociation, the energy level gets very close the one to the other such that the difference in between two consecutive levels at this limit tends to 0. So what we are going to start with is we are going to calculate delta G bar. Delta G bar must tend to 0. Why? Because we know that the difference between energy level decreases till it tends to 0. So we write the general formula for G nu plus 1 minus G nu. We just substitute. We have already seen this part. We expand a little bit, okay, and we try to make it equal to 0. But before that, you can see that Xe, we have said before that Xe is very, very small. Because Xe is very small, so we can take here nu bar common, we will get 1 minus Xe. So Xe is very, very small, so 1 minus Xe is approximately equal to 1. So you can see it this way. Or you can say that Xe is much, much smaller than 1 multiplied by nu bar from both sides. So you will get nu bar is much larger than Xe nu bar. So we get rid of this part and we are left with a nu bar minus 2Xe nu bar nu. So now if delta G tends to 0 at the energy of dissociation, put it equal to 0 and try to find this nu. Nu, this is the nu max. We have said that the energy of vibration cannot increase indefinitely. It must increase to a maximum because after that there's a dissociation. So at dissociation, we are calculating a nu max. Nu max, as it appears, it's equal to 1 over 2xe. Now, if we are searching for the dissociation energy, it's simply G bar for this nu max. لأنه الجي بار إذا بعدكم فاكرين هي الويف نمبر أو الانرجي كويف نمبر والدي هي dissociation energy أوكي كمان كويف نمبر. So simply just substitute كل اللي بنعمله substitute for new بقيمتها النيو ماكس اللي نحن لقيناها اللي هي 1 over 2xe. This is what we have to do. That's it. So substitute, do your calculations, arrange, you will get this form. Now this term here is much larger than this term here. Remember that Xe is very, very small. So dividing by Xe is for sure much larger than multiplying by Xe. So this term is cancelled and we are left with this term for approximation that dE, which is the dissociation energy, is equal to nu bar over 4xe. Or we can write it this way, nu bar squared over 4xe nu bar. So in this case, we have the unharmonicity constant as function of centimeter minus 1 or as a wave number. هلا بيرج-سبونر عنده طريقة انه يحذر فيها الديسوشيشن انرجي لانه اذا عرف الديسوشيشن انرجي مثل ما شايفين احنا بنقدر نعرف من الديسوشيشن انرجي بنقدر نعرف الانهارمونيسيتي كونستانت. So طريقته هي كالتالي. إذا نحن قادرين نعرف ال energy of absorption أو ال absorption wave number ما بين 2 levels so ما بين الصفر والواحد الواحد واثنين اثنين وثلاثة إلى آخره. إذا قادرين نعرفهم لهدول وهلأ نحن بنعرف أول كم واحد، البقايا ما راح يبينوا معنا experimentally أكيد. إذا قدرنا نعرف نحن أول كم واحد نقدر نجمعهم مع بعض، نحن بنعرف إنه مجموعهم كلهم مع بعض راح يعطيني دي زيرو. ليش الدي زيرو مش الدي إي؟ لأنه الدي زيرو هي ما بتبلش من الليفل زيرو، الدي إي بتبلش من الأرض. أوكي، من كعب الويل، من كعب البوتنشال انرجي. شو بعمل أنا؟ أكيد نحن بنعمل بلوت بنكفي الجراف تقريبيا. هلا هو منه 100% بس بيعطي approximation لل dissociation energy وقريبة على ال experimental value. بس دايما لأنه نحن بنعمل approximation by a linear line مش مثل true line، فبتطلع عنا ال approximation شوي أعلى من ال real value. This is not in the course, so just general information for you, but this is one of the methods that Burge-Spooner uses in order to calculate the dissociation energy. Okay, so he just does a plot and assumes لما عندي الدلتا G tends to 0 كيف بصير عنده الانتجريشن أو السميشن. شوفوا كيف كل ما كبرت النيو كل ما الدلتا جي يعني الانرجي راح تصغر، الفرق بالانرجي بيصغر لحد ما يصير صفر. اوكي، سو السميشن لنيو دلتا جي بار هي نفسها الانتجرال للجراف اوف دلتا جي دي نيو. كانوا عم بعمل انا انتجريشن يعني عم جيب الاريا للشكل اللي انا معي. Now, as I have said, the values obtained by the formula of Burge-Spooner are relatively close, a little bit higher to those obtained experimentally. So these are the values obtained with Burge-Spooner formula. This is the vibrational wave number of these molecules, and this is the unharmonicity constant for different molecules. أكيد هيدول values were found using the formula TE bar is equal to nu bar squared over 4 nu bar xe or xe nu bar. So using this formula, which is the formula of Burge-Spooner. Okay. This is the last topic in this chapter about Boltzmann distribution and why the level nu equals 0 is the most occupied level. So the vibrational energies depend only on the quantum number nu. As you have seen, the energy depends on nu. Same for the vibrational function, thus the degeneracy for the vibrational energy levels is 1. So the degeneracy is 1. It's simple. If the spectrum is observed in absorption at ambient temperature, the intensities of transitions decreases rapidly as nu increases because the population and nu is related to n0 by the Boltzmann factor. So as you can see here, contrary to the previous discussion in the case of rotation, here J nu and J0 are both equal to 1. So there's no coefficient that depends on the quantum number nu. The only dependence on nu lies in the energy. And when the energy increases, the exponential will decrease. Okay? So the energy spacing between the vibrational energy levels is typically in the order of 2 times 10 to the power minus 20 joule per molecule. So this is the difference in energy between two vibrational energy levels. So with Boltzmann distribution, one can calculate the number of molecules in the level nu equals 1 state. So let's calculate how many are found in the level nu equals 1. With respect to the molecules that are found in the level nu equals 0. So all we have to do is n nu equals 1 over n0 exponential minus. So simply the difference between the two levels, he said that the difference between two levels is approximately 2 times 10 to the power minus 20 over, this is Kb, the Boltzmann constant, and this is the temperature. So the answer turns to be 0.008%. So this means that approximately 0.8% of the molecules are in the state nu equals 1. which is very small. كمان للليفل 2 رح يكونوا أقل وال 3 أقل. هيدا إذا بالواحد كانوا بس 0.8. So at ambient temperature, at room temperature, أغلب molecules are found in the energy or in the level nu equals 0. Okay, so that's why the transitions from the level nu equals 0 are of major importance. They are the most important transitions and they are the most observed in the